We are very happy to have Yu Cheng from USC today. Yu Cheng is a PhD student advised by Teng, and he's interested in algorithmic game theory, spectral graph theory, and has some really cool papers on these topics. Today is going to talk about information revelation.
Cool. So I'll just start. Feel free to interrupt me at any time. We'll start with something. It's called an Ace King Queen Poker Game. This is a game I actually learned as an intern here from another intern called Will Ma. So he teaches poker at MIT and won a major tournament. He won like $2 million overall, but now he decided to pursue a PhD, and we interned that same summer. Yeah. So this is a game I learned from him. It's a simplified poker game. There are only three cards: ace and king and queen. Only three cards in the deck. Alice and Bob each puts $1 in the pot. They can take a bet. It's empty, and Alice has the option of betting another dollar or not. Okay. If she chooses to bet, then Bob can either call or fold. Right? We're gonna look at how you will play this poker game, and then I'll tell you why it's related to everything I want to say today. Okay. So what if you're Alice and you hold an ace? What would you do? So you know that Bob is either holding a king or a queen, right? You will never lose, so you will bet $1, right? It's dominating to try to win an extra dollar from it, right? Okay. One interesting thing is what if Alice is holding a king? What would Alice do? When Alice is holding a king, Bob is either holding an ace or a queen, right? So Bob would always call you with an ace, and Bob would never call you with a queen, right? Because higher card wins. So actually, when you're holding a king, when Alice is holding a king, it doesn't make sense to bet at all, because you will only get called when you're beaten, right? Okay. The last part is what if Alice is holding a queen? So we know that she will always bet with an ace. She will never bet with king. What about when she's holding a queen?
It's to pretend she has the ace when the other guy has the king.
So she will bet with some probability, depending on the payoff structure of the game. So in this game, she will bet with probably 1/3. And that's called bluff. That's the optimal way of playing this game. And Bob would call with an ace always, catching her bluff. And with a king, Bob would fold with probably 1/3 and call the other situation. So two takeaway from this example. One is that if you actually play poker, when Will present an example, the message is you should actually bet with your best hands and worst hands. You bet your best hands for value, and you bet your worst hand to bluff people off. Right? When you hold a middle hand, you should actually just call and not do anything. The second thing is there are many aspects of this game that you will see again and again through this talk. So one is it's a game with uncertainty. Cards are dealt randomly. Two, people have private information. You know your own card, but you don't know your opponent private information. So three is there's a signaling scheme here, right? Like by betting or not betting, Alice is revealing something about her card to Bob. So this is the setting that this talk is about. This talk is about what is the best way to reveal information, and specifically what's the computational complexity of revealing information. This is based on mostly two papers, one EC and one Fox paper, and I'm lucky to work with lots of people here, received guidance from many of them and many young minds as well. And let me state this three things again. So first we have a game with uncertainty. Then the agents have misaligned incentives. So their choices will depend on the information that's available to them. And you have an informed principle. So here it deviates away from the poker setting. You have one party that knows a lot more information than everyone else. And this principle is trying to reveal information carefully to induce a desirable equilibrium. Okay? Examples like this includes poker and ad auctions. For example, Google knows a lot more about the user than the bidders, and Google is trying to reveal partial information about that to the bidders to maximize revenue. When you use Google Maps know more about the traffic than you do. but you're selfish. You want to get there as fast as possible. And when you're graduating, your advisor writes a letter for you. Your advisor knows better about you than the institution that's trying to hire you. So your advisor can choose to reveal partial information about you to help you, right? So these are the two major ways of influencing the behavior of other people. One is through designing incentives. That's the field of traditional mechanism design. You promise someone, for example, you're running a second price auction, you promise him if you bid the highest, you're going to get an item. And you have a payment rule saying you only need to pay the second highest bid, right? So people will bid honestly because the way you design this incentives and allocation. The other way is through influencing their beliefs that you influence their behaviors. So this is what we call information structure design. And sometimes the task often referred as signaling or persuasion. This is the optimization problem of how do you reveal what information to people to get a desirable outcome. Okay, so this talk is going to cover two basic family of games, network routing games and zero-sum games. And then towards the end, we're going to see some ongoing work and more applications. So we'll start with network routing game. Let's go back to the Google Maps example again. So let me revisit the 3 points here. One, there's uncertainty in the network. Every morning you wake up, the congestion of these roads are going to be different. 2, Google knows better than you do. 3, after Google revealed information to you through these colorful things, you're going to pick the shortest path. You just want to get to work as fast as possible.
It is not a good example because no one drives in New York.
Yes.
But it's okay, but California would be a good example.
Yes. Well, variance in California is also much higher than other places, but not high enough. Well, we don't have public transportation, so like, you have no choice. Right. The question of how to reveal information optimally becomes how do you reveal information to minimize the latency of selfish routing. So we'll go through 2 quick examples, and then I'm going to show you the proof outline for this work. So one is, let's say you wake up in the morning, very simple example. Nature flips a coin. You either get the network on the left or the network on the right. Okay? Google knows which one, because Google is monitoring the congestion. Drivers don't know. Drivers only know 50-50. So what would Google do in this case? The latency function are constant in this case. So no matter how many people take the routes, they're always going to be 0 and 1. In this case, Google would reveal full information, tell everyone to go on the 0 link, and everybody would be very happy, right? So this is very intuitive. This is usually what happens is more information induces higher efficiency, right? But the second example is slightly a bit counterintuitive. This is a variation of the famous Braess paradox. So if this middle link has latency 0, then it incentivizes people to take the zigzag path. So the social optimal way to route is actually for half of the people to take top and half to take bottom. They each incur a latency of 1.5. But when you build this extra highway in your city, actually it made everybody's life worse. And they all suffer a latency of 2. Now, think of the middle edge as a bridge, right? It's a very wide bridge, but half of the time it's up and half of the time it's down. When it's down, you can use it as 0. People will use a zigzag path. When it's up, it's infinity. People will go back to social optimal routing. So if you're Google, you know the bridge is up or down. Do you want to tell that to the drivers? If you do, half of the time you're getting a zigzag. So half of the time you're getting 2, half of the time you're getting 1.5. That's worse than revealing no information about this bridge. Just tell the users, I don't know whether the bridge is up or down. Right? And then that's enough to deter people away from using this bridge. And half of them would do top, half would do bottom, and life is good for everyone. This is the, I would say something that potentially, I don't know, like how useful is this? And clearly Google Maps is very mysterious to me. It does a lot of things that I don't understand. These days, it has this similar ETA thing, but sometimes you switch, you actually see quite different times. And I think back in the old days, Waze is very public about this. they would send people to longer paths just to get a better information on that route, because you don't know, right? Just because you don't have enough people driving on that route, so you don't know. So this sort of encourage people to explore. They're open about it, but a lot of things about Google Maps that I don't know. I know one thing is if two people search the same starting and ending point, sometimes they get different recommendations. When you have two passes of similar latency, let's say. Yeah, very exciting. Right, the results here, the theoretical results is actually NP hard to get a better approximation than price of anarchy. And in the worst case, what you should do is just reveal for information. Right? We're gonna see a sketch of that proof very quickly.
No, sorry, what's the setup? The setup is that you choose the signaling scheme, then you compute price of anarchy for that signaling scheme, and you want to find the price of anarchy that the signaling scheme minimize price of anarchy.
You choose how to reveal information. That is, you can choose how to combine these networks, right? And once you reveal information, players play selfishly. You compute the Nash flow in polynomial time, and you compute the latency of that Nash flow. So you take the expected latency across your signaling scheme. That is the quality of your solution. Okay, and you're comparing to the optimal,
the social optimal given for information.
No, sorry, you're comparing to the best signaling scheme.
Okay.
Yes, you're designing a signaling scheme and you're comparing against the best possible signaling scheme.
So the approximation ratio is price of anarchy over price of anarchy.
Yes, it's comparing to Nash flow. The Nash flow of your signaling scheme and the Nash flow of optimal signaling scheme.
You're doing
just latency.
Non-atomic.
Just latency. Yes, we're doing non-atomic. Yes.
So yes, you have uniqueness as you can do Nash flow. Okay.
Yes. There's a canonical equilibrium, and you can compute it polynomial time. So once you decide on the signaling scheme, the quality of that signaling scheme is computable. It's well defined and computable in polynomial time.
Is saying that you don't know a valid move, or do you have to tell the user?
So you have to choose to tell them something, but revealing no information just means give them the prior.
I see.
Because they have right. So, So the construction. This is a sketch of the proof. Basically, you would construct a graph that's a 2 copy of your given graph, and let's take the Braess paradox example. So I'm going to construct a graph with 2 copies of Braess paradox with a super source and super sink. Then let's say I design it in a way that exactly one of these links are broken. So every day you wake up with some probability, one and exactly one of the link is down. Google knows which one, but the players just know one of them is down. Okay. And what is the optimal signaling scheme for this graph? This is the optimal. Well, this is one of the optimal signaling scheme. Is you partition your edge into 2 sets, the red one and the black one, and you only tell the user which set the broken link belongs to. Once the user sees, for example, one of the red link breaks down, then he will take the green route, which is social optimal on the bottom half of the graph. You can tune the probabilities so that this becomes a network design question. Essentially, Google is facing whether or not to reveal information about this edge. That decision corresponds to whether you want to keep this edge or remove this edge. And that problem is NP hard. It's a network design problem. Which set of edges you want to remove from a network, that Nash flow is, latency of Nash flow is minimized. And that is hard to approximate better than 4/3 as well. So we use that as a black box. That concludes the Google Maps part, and we're going to move on to zero-sum game. Questions? It's not very long. This is like a 2-3 pages proof, essentially following this intuition. Okay. Yes. So this is not a zero-sum game, but this is a normal form game setting that we focus on. So say you have a prisoner's dilemma. I'm not going to explain this, but the only Nash equilibrium in this game is both player with defect, unfortunately. And let's say now you have a godfather in this game that likes people to cooperate. So the godfather would Well, actually, no. The Godfather just have a mood today, and he will add he'll give the player who cooperates extra theta dollars. Depending on the mood of the Godfather, this is a uniform number from either 2, 0, or -2. Okay? Punish or encourage cooperation. And if you stare at this game, first thing you can see is whenever theta is at least 1, so you can compare these two blue values, for example. When theta is at least 1, it's enough to incentivize the players to cooperate. Okay. Let's say the principal is nice. The principal will guess $1 if they cooperate and 0 otherwise. Okay. You are the principal. You know the exact value of theta. Players only know a prior distribution. How would you reveal theta? Let's try the two very simple signaling scheme, no information and full information. When you reveal no information, players going to take theta as risk neutral players are going to take theta as its expectation. So that's 0. They never cooperate. When you reveal full information, whenever it's 2, because it's higher than 1, they cooperate. So you get $1 1/3 of the time. So expected payoff of the principal is 1/3. Right?
So
Can you do? Yes.
Sorry, I didn't quite get that. When
theta
How does the
theta is uniform 2, 0, -2.
how does the principal get paid? I think I thought he was only paying them.
Okay, so the principal is not paying them. They're playing this game.
Okay.
And principal has a utility over their actions on this game. The principal is happier when they cooperate.
So when you say information, do you mean the setting of theta or something else?
Principal knows theta. The prior,
I see. So that's the information revealing.
Yes. You can choose how to tell them.
Got it.
Okay. Yeah.
yes.
Sorry. There's no cost to setting theta.
No, there's no cost of setting theta. And you don't decide theta. Nature decides it. You just learn theta from nature. Right? So these two are, say nothing. Honestly tell them what theta is. Okay? Turns out you can do better in this case. You can tell them when it's 0 or 2, you tell them it's 0 or 2. And when it's -2, you tell them it's -2. Right? That's the signaling scheme you're going to use. And conditioned on it being 0 or 2, its expectation is actually 1. And when that happens, that's enough to incentivize them to cooperate. So they cooperate 2/3 of the time. You get double. You're twice as happy as before because they cooperate more often. So this is sort of the game we're going to focus on. So essentially, the input to the problem is a list of normal form games. And the principal has the option of choosing how to combine them. Then receiving the information, the player would do a Bayes update and play a Nash equilibrium using the expectation of theta, replace it, and play that game. And the principal has certain objectives. They want them to play the game in a certain way. So for this talk, we're first going to restrict it to zero-sum games. Just to make everything simpler, the upper bound extends to general sum as well. So let's say a number of games and the number of strategies are both n, just to make things easier to talk about. And the principal is trying to help one of the players. Think of this as advisors trying to help a student and students playing a zero-sum game with an institution. The upper bound says there's a quasi-polynomial time approximation scheme to compute an epsilon optimal signaling scheme. Okay, I'm going to very quickly sketch how do you do this in quasi-polynomial time. Note here, this problem is in NP because you can show that, well, given the signaling scheme, you can compute its quality, just like in network routing games, because the equilibrium in zero-sum games is well-defined and has a unique payoff. So what happens is I'm going to draw a simplex and essentially get 3 different games at the vertices of this simplex. And the blue region is a game at this point, averages the 3 game in a certain way. And the blue region are the region where the expectation of theta is at least 1. This is a region, if you reveal a posterior in the blue region, they're going to cooperate. Right? So the question becomes, how can you decompose this prior so that you get a blue point with highest probability? Right? So the no information scheme corresponds to reveal the prior, reveal the x, so red point, so they never cooperate. the full information scheme corresponds to decompose it to 3 vertices. You always tell them exactly where it is. And you get a blue point 1/3 of the time. The optimal signaling scheme decompose it into these 2 posteriors and mixes the game when it's 0 and 2. So you get a blue point 2/3 of the time, and that's the best thing you can do. So essentially, a public signaling scheme in this setting and in many other settings corresponds to a problem of computing a convex hull of this underlying function. Okay. So now to show you, let's make everything formal. So mu1 and mu2 are the posterior that I used. I mixed 2 of them, and the other one I reveal you complete information. And the optimal signaling F applied on a posterior gives the principal's payoff under that posterior. The problem becomes computing a F plus of lambda. Okay, just a linear program. So the takeaway from here is if I can promise you the set of posteriors that you will ever use, then you can solve a linear program and done with it. So to show you there's a quasi-polynomial time approximation scheme, all I need to do is to show you there's a epsilon optimal signaling scheme that only uses signals from a quasi-polynomial size set. Okay? Those are the set what I call log n sparse signals. Sorry, these are signals that you take a log n multi-set, and you can convert that into a distribution. If you've seen the approximate Nash, this is very similar to that. So given the trick is, given a signaling scheme that uses arbitrary posterior, I'm going to convert it to a signaling scheme that only uses sparse posterior. So what happens is, given a posterior, it describes a way of mixing these games together, right? For example, in our example, this is half and this is half, right? It mixes the first 2 games. And the idea is you can sample from this mu, pretending it's a distribution, and get a mu tilde. Instead, this mu tilde is log n sparse. And you use standard tailbound and union bound to say when you sample log n times, all the entries of a mu is going to be preserved up to epsilon. And you know that a mu is a zero-sum game as well. It's the posterior zero-sum game. So if all the entries are within epsilon, you know the value of that game is within epsilon of the original game. So what you do is you take a signaling scheme, you convert it to another signaling scheme of roughly the same quality, but now it only uses sparse signals. That shows you can solve an LP and be done with it. So the result that I'm more excited about is this algorithm, as simple as it is actually tight for this case. So there's a matching lower bound based on either Planck-Lee conjecture or exponential time hypothesis to show that it requires quasi-polynomial time to compute a signaling scheme. Today, I'm going to show you a reduction from Planck-Lee conjecture, just because it's easier to follow. So
what was the other hardness from?
This one? ETH.
Time.
Yes. If you assume it takes 2 to the order of n to solve 3 sec, then this problem is, and you can solve it in some.
Either of these is stronger than the other one?
We don't know. It's open. Okay, but people generally like ETH better because it's worst case.
And when you say Planck-Lee, I'm asking this because when you say Planck-Lee conjecture, do you use like single Planck-Lee problem or like partitioning into problem, like covering the graph? Which one?
You use they are the same thing. You use the you start from the single one, but then you reduce it to partition into.
Okay, so you have that.
Yes. So it's the same thing. It's in Chadin's box paper as well. It's just tightens that result. So actually, I'm not going to explain the extra step. I'm just going to explain Chadin's construction of that game. Right. So to show that it's hard to reveal information, all you need to do is construct the instance that's hard. So this is a game that we're going to try to construct. So it's a security game. Theta is a treasure that's hiding somewhere on the graph. The principal knows where exactly theta is, but the row and column player only knows it's a uniform node on the graph. Okay? Right. And the row player wants to be adjacent to theta. Whenever he's adjacent to theta, he gain 1 point. Okay? And the column player wants to catch either rho or theta. So the column player has to hit the exact same node, either r or theta, to defend the treasure. Okay? So let me state this formally. So whenever there's an edge between theta and r, the rho player gets 1 point. And 1 point is taken away from him whenever the defender defends either theta or a. Yes.
Okay.
Yes. So 1 point for being adjacent, and -1 point for catching either one of the point.
Okay.
For example, if this is the outcome of the game, theta is actually here, rho player here, column player here. The rho player will get 1 point because he's adjacent to theta, and none of them are caught. If rho is caught but rho is adjacent to theta, for example, gets 0. So this is zero sum. I'm only defining rho players payoff because it's zero sum game. Okay. Turns out revealing information in this game is very hard, as hard as Planted Cleek, for the following reason. We can do a sanity check over the two very simple signaling scheme. So the principal can reveal no information. That is, the principal says, I don't know where theta is. You do your best guess. Then it's very hard for the rho player to be adjacent to theta when the graph is not super dense, right? Because rho doesn't know where theta is. Theta is a random node in the graph. Okay, so that's bad. The other option is he can tell both players where theta is. He reveal full information about theta. That's bad too, because the defender, the column player, can just sit on theta and always catch the state of nature. So the rho player always gets something. The rho player gets 0 as well. You will choose something adjacent to theta, but the column player catches the nature. So
the principal's payoff is what?
Say that again.
Principal's payoff is what?
It's rho player's payoff.
Rho player.
He wants to help rho player.
Okay.
Help one of the player. Because it's zero sum game. Social welfare doesn't make sense. It's always 0. So he helps one of the players. Okay. So to show hardness for revealing information in this setting, just consider what happens when you have a complete bipartite graph. Okay? You are the principal. You know where the treasure is. You want to take advantage of the symmetry in two players' payoff. And what would you reveal here? Okay. Turns out what you can do is you can tell which side, either the left or right, which side theta is on. And the rho player will choose a uniformly random node on the other side of the graph. Why is this a good situation for the rho player and principal? Because they will always be adjacent to each other, right? It's a complete bipartite graph. And they're both randomizing over a large set of points if this bipartite clique is large enough. It's very hard for the column player to catch them. Right? So the payoff when you have a k by k graph is actually 1 minus 1 over k. It's very close to 1. Okay? So then we're pretty much done. The intuition is done. The actual proof is actually quite long. But the intuition is that cliques are good for the principal and rho players. So the optimal signaling scheme corresponds to a partition of the given graph into dense subgraph. And that problem, you can imagine that you're given a random graph, a g½, embedded many cliques in there, and you want to partition them into cliques. And that's as hard as identifying just one planted clique. And then we're done. So if you know how to do optimal signaling, you get an algorithm that reveals a clique in a random graph. And that we don't know how to be quasi-polynomial. Okay. So yes. So questions? Wrap up the zero sum. Okay. Okay. Cool. So so in the third part, I'm going to tell you something about other applications in the signaling domain and some future work when you can privately reveal information to people. You don't have to announce publicly information. Like sometimes the principal becomes more powerful and can get higher utilities, better outcomes.
So here the prior on theta is uniform prior?
You can have any prior you want, but it's a common knowledge. Everybody knows the same prior. It doesn't have to be uniform, but usually it's the same thing.
Okay, so because you're talking about optimality's hardness, right? The approximation anyway, you get very close to optimal. You get 1 minus epsilon, and so it doesn't matter what prior you have, all the priors you're getting. Okay.
Yeah. The upper bound works for all prior.
Yes.
For lower bound, we use uniform. It doesn't matter, right? Okay. So, so last part is essentially just 2 examples. One is you have a Bayesian second price auction. So the auctioneer is selling a random item. It could be one of these 4. Again, bidders don't know which one it is, but the auctioneer knows exactly which one it is. The auctioneer is committed to run a second price auction after he reveals information about this item. Okay? So sanity check, 2 signaling scheme. If the auctioneer reveals exactly which item it is, you get 0 revenue. Because one player bids 1, everybody else is not interested in bid 0, you get 0 for revenue. And if you reveal no information, you just tell them it's a random item, they bid a quarter. That's their expected value for a random item. And your revenue is a quarter. Okay. So what's the best thing you can do here? So you can get half. You partition the item into 2 sets, and you tell them it's the first 2, it's one of the first 2 or one of the last 2. Okay. And 2 of them would bid half. They would compete against each other, you get half. Okay. So then you can ask the question, if I have a more complicated matrix than this one, how can I extract the maximum amount of revenue? So let me denote the F again. This is a posterior. So this is a no information posterior. This is the optimal, one of the optimal posterior. F maps it to principal's utility in that case. And second price auction is simply setting F of mu to the second largest entry of A times mu. Okay, and this is solved by separately by Emek et al. And Milterson and Chaffet. But it was left open that what if, instead of knowing who exactly my bidders are, what if I only know a distribution of them? Think of that as I know the valuation of 1,000 people, but 100 of them is going to show up randomly to my auction, and what should I do in that case? So that remained open for quite some time. And we solved it by using essentially the same technique of showing that you only need to use sparse signals and then solve an LP over them. The reason why you need to essentially you sample this mu to preserve the value of this function. To preserve value of this function, you only need to preserve the largest entry and second largest entry. So you can even get away with not taking the union bound. So instead of getting a quasi-polynomial time algorithm, you get a p-taps instead. And it's actually, there's a general framework behind all of these signaling problems. When you have an auction, Bayesian auction you want to run, you care about this function. When you have a Bayesian zero-sum game, you care about this function. You choose how to mix the A's together, and you care the value of this zero-sum game. And you can design other situations like people are voting, and you can choose what information to tell them, so they vote yes or no, and you want to maximize the number of people who vote yes, say. So it turns out there's an algorithmic framework that samples the posterior and solve these all of these problems. And it's very nice. This turns into a Fox paper, and that solves quite a few open problems in game theory. Okay, so the last example I'm going to talk about today is what if the principal gets the privilege of privately communicating with each player? Okay. And again, we go back to the Google Maps example. I'm going to show you that there is a case a principal can do much better, well, a lot better compared to the case where he can only publicly announce something. Okay. So we're going to look at a variation of the Pigou's example. This is an example that gives you the price of anarchy and Nash flow and social optimal. So in this case, the social optimal is for half of the people to take top, half takes the middle, right? So, but in reality, people would all take the top pass, and they will only stop until all of them are on that pass. That's the unique Nash equilibrium. I'm going to augment it with a path with congestion infinity, and I'm going to rotate it. Okay? So you wake up in the morning, it's one of these 3 networks. You don't know which one, but Google does. Okay? So if Google can only announce something publicly, then I claim the latency is at least 1 for everyone. For example, Google can reveal phone information, tell you which network it is, and everybody will take the X path and gets a latency of 1. If Google ever tries to mix up 2 of these networks, let's say with some probability it's the first one, with some probability the second one, then what happens? Because this link has infinity, people are only going to take the only edge that's not infinity on either side of either one of the graphs, right? So if I have a public signaling scheme announces things to everyone, then everyone will take the same path. If I reveal full information or if I ever try to mix them, I don't do very well, right? Effectively, I get 1, which is what I get when I reveal full information or no information. Actually, when I reveal full information, okay? So what's the private signaling scheme you can do here if I can recommend different route to different people? So it turns out it's very simple. You just signal the social optimal flow. If this is your graph, tell half of the driver to go top and half of the driver to go middle. Okay? We're going to see why it's incentive compatible here. Let's say you're a driver. You receive the recommendation to take the middle path. What do you know? You know with probability half, you're on the first graph, and with probability half, you're on the second graph. That's all you learn. You know for sure you're not on the third graph because Google would not recommend that path to you when that's the case, right? 50-50, okay? You don't want to deviate because half of the time you're on this graph and half of the time you're on this graph. If you deviate either to the top link or the bottom link, then with 50% chance, you're going to suffer a latency of infinity. And you don't like that. So you will follow Google's recommendation. Essentially, the full revelation scheme here is Bayesian incentive compatible. So players would follow the recommendation. And the gap between public and private signaling scheme is 4/3 in this case. That's the maximum you can achieve because you can always reveal full information. Okay. So that concludes my talk today. To summarize, we settled the computational complexity of revealing information optimally in network routing games and Bayesian zero-sum games. And we see a cute example where private signaling scheme does better than all public signaling schemes. That's it. Thanks. Yeah.
Hey, quick question. For the zero-sum games, is there just one notion of optimality, or is there a whole bunch of them?
Yes, good question. When you have a zero-sum game, it's actually just one fixed notion. Because once you fix the signaling scheme, you can evaluate the quality of it, right? You get a bunch of...
Well, hold on. So is the principal somehow trying to get them to cooperate? That was one of your examples.
The principle, yes. Well, in a zero-sum game, if you care about social welfare, it's always 0, right? So the example I used, you care about the role player's payoff.
Okay.
And that's fixed. After you reveal the signal, there might be multiple equilibrium, but the role player gets the same payoff in any of these equilibria.
Okay.
Right? So it's well defined. When you have a general sum game, it's tricky because after you reveal the information, there's a general sum game. And there are multiple equilibriums of different results in the general sum game. Let's say you want to maximize social welfare. The assumption we make is you can recommend the equilibrium when you send the signal. Let's say I tell you it's either one of these 2 games and I recommend you to play this equilibrium. The player can check that this is actually an equilibrium, and then they can play following that. That's the optimistic view.
Okay.
There's robust notion as well, but we can handle that too.
Got it.
So that's why in this talk I choose to focus on zero-sum games, because equilibrium computation is unique and canonical for zero-sum games.
So for this auction question,
yes.
like you had this example. I think that's relevant to like the Google setting of what you can signal.
Yes.
So there, have you considered this private versus public and thought about what is the most meaningful question to study?
No. So that would be
because I can even think of like signaling buyers what exactly they care about the most and extracting the maximum bits from them, like differentially signaling, etc.
Right. I don't know. There is a paper in EC last year by Daskalakis, Papadimitra, and Samos on if you want to combine the two problems. You can design the signaling scheme. You can also design what auction you run after that. Then this problem is equivalent to the multi-item auction. Instead of selling a random item, you're actually selling M different lottery to different items. And then it's multi-item auction, right?
Okay.
But that's different from what you're asking. So I don't know. Yeah, it's open, for example.
I think that's a good question to consider because it's,
yes. Well, right.
It's likely both theoretically interesting and definitely practically interesting.
Yes. Well, I'm not sure. Like, would you say the commitment to running a second price auction afterwards is realistic? Is that because you want to do Meyerson, right? Like you actually want to do Meyerson, but
no. I mean, we fix certain things. Yes, the second price auction is sort of set on stone. It's because that's what the exchange does all the time. So that is reasonable.
Then I would say I don't know.
Okay.
But that's very interesting. I don't know. For example, a cute example would be: do you have an example of an instance where public signaling in Bayesian second price auction does much worse than private signaling?
Exactly. Yeah. I mean, to be clear, I mean, I'm thinking of a setting where, like, the item that comes, I mean, it's the same item, right? It's and then like people don't know the features of the item. There is like it's a multi-featured item.
Yes.
And let's even think of a setting where the value is just the inner product of a vector you have. Each pair is a vector. It's a WI for player I,
yes.
And then feature is some Boolean feature vector X, and then inner product of WI and X is like VI.
The value for the bidder.
The value for the bidder. What you want to do, like, okay, one extreme is just doing the best things for each guy, but then you lose some tension there.
Yes.
There's a way to formulate this problem so that there is like some tension in the problem.
Yes. I know.
Like perhaps we should also put restrictions on like how different you can be when you're talking about private signals, right? Like you can't lie or something. Like you can. Maybe you can report a 0. I mean, you can't report a 0 to be 1, for instance, and things like that.
Right.
So you can maybe report a 1 to be I don't know, but you can't report a 0 to be 1 because that's like saying.
Yes. Yes. Yeah. A lot of this is built on you're playing a repeated game, and the signaling scheme is something the other party, the players can verify. Think of it as Google can publish the code of how Google Maps actually recommend suggestions. People can verify that code.
So the 0, 1 infinity example, is that lying? It is,
no,
right? No, it's not.
No, it's not. You can, okay. So it's not more lying than the bluff case in the poker game. For example, if you know for sure, for some reason, that you're on this graph, then you actually should deviate to the X, right? Because half people is on that path. If you know for sure, for some reason. This is the same argument as if you know for sure Alice is holding a queen, you should call with a king. But overall, you shouldn't. Well, you shouldn't always call with a king, at least, because sometimes you catch Alice bluffing, sometimes you suffer very much, you lose money. So if players are risk neutral, they will not deviate. But if there's leakage, let's say I learned I'm on this graph from some other app, then all bets are off, right? Right. For your question, I know there are work that studies the following setting, where every player can either choose to vote yes or no, or buy an item or not buy an item, and the principal just cares about some function, say a submodular function over the number of people who buy the item. Okay. A simple example would be I just care the number. My utility is the number of people who vote yes. or the number of people who buy the item. There's a hardness result if that function is submodular. So the best you can do is to signal privately. So this is called, I think it will get into EC this year, but the result's not out yet. It's on archive. It's by Shadin and one of his students. It's called private Bayesian persuasion.
Private Bayesian persuasion. Okay,
and
then you think you care about how many people purchase the item, right?
Yes.
And then you are motivated to, therefore it's a monotone submodular function, and you want to motivate as many people to buy it as possible.
Yes.
And what is the information structure? Like, what are you revealing?
You can tell each player different things about
like, but what is
but you can't lie.
What is the information structure? Like, what are you lying about, or what are you saying?
You're saying something about this random item, right? It's a random item.
Okay, it's the same setting.
It's the same setting.
Okay.
Except instead of caring about the second highest bid, you care about the number of people who buy this, who choose to buy this item.
Okay.
Yes. You can, so think of it as there's a fixed price, I think.
Which means the number of people who bid one or something.
Yes.
That's what you care about. Like, ultimately, there's only one item, right?
Yes.
One item, but you care about the sum of, like, the number of people who bid one for this item.
Yes. In their setting, think about I'm trying to sell a software or something, a copy of some item. I actually have unlimited, but the more I sell, I get a diminishing return function of these things. And,
okay.
Yeah. So essentially, you suffer the 1 - 1 over E because you can be running a very complicated correlated signaling scheme. And when you turn that into independent, you suffer this correlation gap for some modular functions.
Okay.
And the best you can do is to optimize overall the independent signaling scheme. Basically, for you, I'm going to flip a coin and tell you something about the item, but that's not going to be dependent on what information I reveal to other people. I'm going to flip different coins, but they're independent. If you want to beat that, then it becomes NP hard, just maximizing some modular. So
it's really cool, actually.
It is, yeah.
Very nice.
I can send you the link to the paper.
Okay, cool.
Thanks very much.
Thank you.